Well, hey, howdy, hey, everybody, and welcome back to Dan's Pro Shop. Today, we are kind of diving in a little bit deeper due to an overwhelming viewer request. That's right, yins, guys. And to a little side project that I got into with the old garage beer fridge. Yins asked, so here we are. We're doing it. Let's dive in and kind of give you a little glimpse on how I did what I did. So just in case you guys missed it, here is that short that led to this video. Well guys, it finally happened. After all these years, the old garage beer fridge finally kicked it. I mean really, ain't that just a... No, do not let this discourage you. We have practiced for this moment. Remember your training. You think we keep all this crap laying out in the garage just because it looks cool? So I got to thinking.
So I rewired it.
You're darn right I rewired it. The temperature control knob in there took a dump, and you can see that we've added some extracurriculars. So I got to thinking, really, all I need is a thermocouple and a relay I can control. So some of you may be thinking, hey Dan, is that a heater control off of an industrial machine? Well, I think the fridge breaking down was probably the best thing that ever happened, because now I can control everything about it. Like my set point down to the 10th of a degree. Added safety timers to keep the compressor from short cycling. And I can program this thing to be normally open, normally closed for the control circuit, and I can do everything right here from the display. So just think about it this way. Next time something breaks, just use that as an opportunity to, Yeah, dude. I couldn't believe it. That was just kind of like a thing that happened. I came out here one day, opened the fridge to get myself a nice ice cold wobble pop, and lo and behold, what do I have? Just a musty, dank, ugh. I probably had to scrap about a case and a half of beer in there because it just literally turned into a dehumidifier, and it's once this stuff goes through a couple heat cycles, it's no bueno. But this fridge, her and I have been together for a long time. Well, I mean, I guess not a long time in the grand scheme of things, but to give you a little bit of backstory, way back when I worked at a mill not here far from where I live, and at the time I was working there, this old girl, this 1960 something Kelvinator, 100% American made in Michigan, by the way, it says so on the back. This thing was in the break room of that mill for God knows how long, possibly from its conception. Who knows? I certainly don't know. But during the time I worked there, they were kind of like upgrading the place a little bit, and they like redid the break room or whatever, so they got all new stuff for the break room. I asked, hey, what's the deal with the old one? Well, are you just getting rid of that? I mean, it still works, so here we are. It's almost 15, 16 years later. This thing has been keeping my irons cold in this garage since then. Yes, it's old. Yes, it's not the most efficient thing in the world, but number one, this thing is a classic. It's a Kelvinator. I really don't think these things are made anymore. It's almost next to impossible to get like OE parts. I mean, yes, you can jerry rig stuff, but it's kind of the reason that we're here. But the kicker is this thing is R12. And if you guys don't know anything about refrigerant, those of you that do, R12 is like the I-Ching. Like, it's like illegal, it's outlawed now by the EPA because like it's known to the state of cancer to cause California. Whatever. R12 is the best gall-darn refrigerant that has ever existed on the face of this earth, regardless of, you breathe it, you might grow an extra toe or whatever. But golly, does it keep stuff cold, and it works freaking fantastic. It was superseded by R134A later on. But this stuff, R12, dude, this is like unobtainium. I mean, yes, it's still around, but it's very difficult to find. So if you have something that's still around and still running on R12, do what you can to keep this thing. And not to mention that this thing has an externally non-fan cooled condenser. So like there are 0 moving parts to this thing. On the back of it, yeah, you got to keep it like 4 or 5 inches away from the wall so it's not the most space-saving unit in the world. But there's no moving parts in this thing other than the compressor. And the compressor on this thing is a solid R12 GE completely enclosed oil bathed compressor. This thing, like, it runs. It's a workhorse. So the whole point, I know I'm rambling here, but you can tell I'm passionate about fixing my stuff, especially when it comes to keeping my irons cold. This thing has an extremely simple control circuit in it. And whenever I found out this thing quit working, all I did was like jump the contact on the side of the compressor to make sure that the compressor was still running. And to my relief, it was. I just hot legged it with 120 and it kicked on. So I knew the compressor was good. It was a huge sigh of relief. So going on down the trouble tree down the line, I'm like, well, figure out what turns the relay on for the compressor. And it's the control knob inside the fridge, you know, where you set your temperature. And that thing is super simple. I will show you how that works. So this little fella right here that I have bastardized and torn apart because of my love of the hunt and diagnostics, and, you know, just fixing something for me isn't good enough. You know, okay, you finished the repair, things are running cool. Most people that would be good enough. Not me. I'm never satisfied with enough. Okay, the part failed. I want to know why. Is it pointless? Most of the time, yeah. But understanding failures is, I don't know, it's kind of like that thrill of the hunt for me. It may be dumb, cumbersome, and over the top or whatever, but whenever something breaks, whenever something fails, whenever something quits doing what it's supposed to do, I thoroughly enjoy finding out the root cause as to why. And this guy here, the temperature control knob thing, or I think what they call it is the cold control, which is a real layman's term if you ask me, but this is basically an adjustable thermostat. I know it doesn't control heat, it controls cold, but let's be honest, it's the same thing. It's something that controls a specific set temperature by a user. This guy is the OE original control for that refrigerator. And since I yanked this thing apart, I might as well tell yins what this thing is about and how it works, because at its core, this is how refrigerators still work. This thing may be a little archaic, but in essence, it's the same damn thing. So this is that cold control that the internet calls it. It's just, it's a switch with some stuff going on here. But you guys see this thing sticking off of here. This is basically just like a thermocouple or a temperature probe. And the way that this works is super simple. This is like any other traditional temperature gauge. The way that this works is that there is a gas, some type of inert gas. It has changed over the years. There's, without doing some research, I'm not going to lie to you, I don't know what's in here. Honestly, it may be ambient. I don't know. But the whole point of this thing is that this tube, which I cut off to get out of where it was just to make it easier to remove, but this tube is hollow, filled with a gas, and it goes into this diaphragm here. So you see this section? This is just like a plenum, for a lack of a better word, with a diaphragm inside of it. So if you guys know anything about like physics of matter, whenever temperature changes, it changes densities of gases. Like they expand and they contract, directly proportional to the temperature that they are exposed to. So the way that this thing works, whenever this gets hotter or colder, the gas inside of here, inside of the tube, the temperature probe, and this diaphragm here would expand or contract based on the temperature on the inside of the refrigerator. And this guy on the inside here, you see that there is a spring way down in there, that compression spring bucked up against the bottom of this diaphragm. So based on the expansion or contraction tension of this diaphragm pressed against that spring changes the tension on the inside of this switch. And on the other side of that spring, that is where your user input gets taken into account. Now, if we look in here a little bit deeper, on the opposite side of the knob, you know, this is where the knob would be, but I'm sure that this thing disappeared somewhere during the Cold War. I have no idea. This is the way that I received it. But you notice on the back side of here, there is a ramp. It's difficult to tell, but that thing is sloped from hard stop one direction to hard stop on the other. You can kind of see it there, that this thing goes up and down, moving that lever on the left-hand side. That lever, being under less or more tension, is responsible for moving the mechanics underneath of that spring to account my user input into and addition to what this diaphragm is doing. So this thing is always constantly working no matter what I do over here, but I can override it by turning it completely off so the compressor ignores the signal of this switch completely, or I turn it on, adding or removing tension to that spring, changing how these levers and contacts work inside of this switch. Now, I mentioned levers and contacts. Let's move over to the part that's torn apart here. So you guys can see here, this is the way that this thing would have looked whenever it was assembled. You can tell I just like tore these ears back with a screwdriver and pulled the contact side of this switch out. So you notice that there is this black plastic lever in here that moves up and down. This is what that bottom lever from the knob input controls, the spring tension on this lever. That plastic lever in there controls the contacts inside of this part of the switch. So I got myself a little pokey bit here to get my fat fingers out of the way. You can see a little bit better what's going on. So inside of here is what we consider a set of normally closed or NC contacts, meaning that from this point to this point has continuity all of the time. I'll show you what I mean. Break out the handy dandy meter here, set it on ohms and continuity. So right now, if I put these two together, we get a tone and a low reading on the meter telling us that these are touching. It's a complete circuit. So right now, if we put this one here and this one here, we get a tone confirming that this is a normally closed switch. That just means if I were to put 120 volts electricity on this side, in theory, I should also see it on this side. Now that we got that little bit of electrical engineering class out of the way, inside of here, this normally closed switch, you see how this works here? There's a little spring-loaded lever, which we would call a contact, and you can tell that this thing is old, beat up, and all carboned like crazy because this thing has cycled a lot over the service life of this thing. The way that this is controlled is by this little black lever in here that is determined by the combination of the spring pressure from the diaphragm and the position that this lever is sitting on the ramp by the user input knob. And this is what controls this lever going up and down based on the temperature of the inside of the refrigerator. Now, the way that this thing would like normally sit, let's say that your refrigerator is idle at 35 or 37 degrees Fahrenheit. This lever would be up, meaning that everything is satisfied. It is what it wants to do. Because, let's talk about the physics of matter a little bit more. Whenever something is cold, particularly a gas, it contracts. Whenever it heats up, it expands. It's just like steel. It's just like wood. Like the most things in our material world, whenever they're cold, they contract. Whenever they're hot, they expand. So think about that in terms of this diaphragm. Whenever the gas inside of this circuit, including the diaphragm, is cold, it will be contracted, meaning that there is less tension on this spring inside of here. It would allow this lever to go up, opening this normally closed control circuit. So whenever your fridge is at temperature, this switch would be open. Whenever the inside of your fridge goes above your set point, let's say you're opening it and loading the fridge or whatever, you're messing around inside of there, the inside temperature of your refrigerator goes up to 40 degrees. The gas inside of this circuit will then start to heat up and expand. Pressing on this diaphragm, applying more spring tension here, and based on where your control knob is here, that's kind of like the straw that breaks the back in this control circuit, so to speak. This switch would then drop due to the spring pushing on it, allowing this switch to close from its other position. So now it would be closed in its normal position, allowing electricity to flow from one side to the other. Whew! All right, guys, I know that was a lot. I didn't mean to be long-winded or whatever, but if you've never seen stuff like this, particularly a switch or like the nomenclature of normally open, normally closed, it's basically a fancy like industry standard way of saying on or off, or like if you're speaking binary, ones and zeros. And let's be honest, the world that we live in is ones and zeros. It's on or it's off. You talk about ladder logic, it's ones and zeros. It's on or it's off. You talk about coding, it's on or it's off. You look at a electrical schematic. I don't care how complicated it is. It could be for a nuclear reactor somewhere. All those lines and dashes and zigzags and everything, it's ons and offs. I don't I know this is a bit of a left field rant here, but people get intimidated by electrical all the time. And like, oh, I don't understand this. And yeah, there's resistors and capacitors and blah, 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 blah. Yes, there is a lot of crazy ancillary stuff that goes on in more in-depth, let's say, digital electronics. But at its core, it is all switches. Let's say I have a limit here. I have a thermostat here. I have a light bulb here. I have a motor here. Everything is controlled by a 1 or a 0. It's on or off at its absolute core. Just like mechanical, like you have a nut and a bolt, or you have a bolt and you have a blind hole, you know. There's an equal and opposite reaction to everything. It's whatever. But what I'm getting at here is this thing is a switch with two states. It is on, it is off. And we can control that on and off based on the input that we give that switch. So in this particular case, we have two inputs, count them, two inputs into this switch that result into one single output. We have the physical temperature reading from this thermocouple, thermometer probe, whatever you want to call it, the temperature reading from the inside of the refrigerator, the input from the physical user, wherever you set that temperature knob, both of those inputs resulting to a single output to this control circuit contact. Now, I know. Now that we've gone through this stupid little thing, you know, this thing no bigger than your thumb, you know, all the stuff that's going on here. Keep in mind, this is old tech. I mean, but this is still widely used now. But like this, you know, if it ain't broke, don't fix it. You know, these things work, and obviously they go bad, but the theory is solid. You know, the logic's there. It's good stuff. But that being said, it's a contact. It's a mechanical switch. It is a mechanical item. Things wear out. Things go bad. You get a little bit of arcing. You get some carbon, bloody, bloody, bloody. It springs wear out. Stuff goes, whatever. The whole point of this thing, I'm sorry. The whole point of this stupid thing is it simply turns on and off the relay for the compressor on the refrigerator. That's it. There is a magnetic contact on the side of the compressor. I would like to show you, but oh my goodness, that thing weighs about 6 million pounds, and it takes 3 men and a boy to move that thing from where it is. And I'm not going to yank it out of there. It's happy, it's working. I'm going to leave it alone. Well, actually, it ain't working now because I have this thing torn apart to show you. But we'll get to that point. But, so, a relay, in case you're unaware, is basically a smart one of these. It uses a magnet to turn on and off a set of contacts. So, the way that this thing works is the compressor on the refrigerator is normally off. Okay, so it's not running, it's not cooling. Whenever this switch gets activated saying, hey guys, it's getting a little hot in here, we need to cool this thing down, this thing activates, turning on the relay for the compressor. So basically, the compressor has no 120 volts AC. Whenever this switch turns on and says, hey, give me some cold, we then put that 120 through this switch to the relay on the side of the compressor. It snaps on, she's running, we got a cold refrigerator. Okay. If you're still with me, I swear I'm sorry, but I love this kind of crap. You can tell it just gets me riled up. It's something as dumb as this, but this is core fundamental crap. Like I mentioned, I don't care if you're fixing a nuclear reactor or a Ferrari or, you know, a 5,000-year-old garage fridge. All of this crap is the same. If you understand the simple stuff, it is what it is. But if you guys saw that short, well, you did. I put it at the beginning of this video. In that short, you saw a control box mounted right here on the side of the refrigerator, which isn't there right now because I tore it apart because I'm going to show you guys how it works. So many of you guys got in the comments of that short and be like, hey, this is awesome. I have a similar situation that I would like to know what you did and how you did it. So for the sake of education, learning, and, you know, keeping beer fridges alive, keeping this stuff out of the landfill, and just keeping stuff running in general, you know, this may not be like the way to do it, but this is the way that I did it. You know, and I realize that not everybody has access to this stuff, and I will try my best to find equivalent things on Amazon that's readily available and something that you can do this for yourself if and when you need to, which, I mean, if you're watching this for anything other than entertainment value, which yeah, I'll see if I can't find a parts list. But that control box thing that's here was clearly 100% homemade. I will show you how dodgy this thing is, but by golly, it works. So here is that temperature controller that you guys saw in the short. And you can tell that this thing is solidly homemade. For any of you residential/commercial electricians out there, you will notice this thing as a simple 4-gang switch junction box. You know, it's I needed an enclosure for something, and this just happened to fit the bill. Now, I will get into this thing and show you what's up, but please have mercy on me for the grossness of the inside of this thing. The way that this thing was birthed. Now, a lot of you guys probably know that I spent almost a decade as the maintenance director at an injection plastic facility. So we dealt a lot with injection plastic machines, and a lot of those have heaters. Well, all of them have heaters. You need to heat plastic to melt it and inject it. Either way, heater controllers are a big thing. This guy isn't exactly like from one of the machines. It's more like ancillary stuff. But I needed a way to like bench test different heater circuits, elements, and whatever. So this is something that I put together probably almost 10 years ago, and I've just had in the bottom of my toolbox, something that I could quickly just test electrical heater circuits and have specific controls and outputs on them. So I could do different tests for, you know, specific temperatures and when I was turning relays on and off and like how heaters would react in different environments and everything. This is just, if you've been a mechanic or a technician or a sparky, or, you know, 9 times out of 10, you end up inventing stuff to make your job better. And some of the times it's testing equipment that, you know, ends up running your beer fridge. But we'll get into this thing and I'll explain what I mean. So let's get some of this crap out of the road here. Get on here. And we'll go through the exterior of this thing just right out of the gate. So here we have a Love control. Now, Love is a brand name. And honestly, I'm not sure if this is an actual brand name Love controller, or if this is one of those like Granger knockoffs. Who knows? I've had this thing for so long, I have no clue. You see here on the right-hand side, I have a fuse holder. So I think in here I have like a 1 or 2 amp or something. I don't know. Oh, 5 amp. Look, I was feeling brave with this particular test. So this is a 250 volt 5 amp fuse that goes in here. And I used this to control the output of this thing because, like I mentioned, this was a bench test item. So sometimes I was hooking up sketchy stuff to this, and in case something went sideways or something shorted to ground or whatever, you know, I wanted this thing to blow instead of the circuit that I was plugged into. So yeah, I guess that's pretty much this thing. You guys can see here that I have a couple KOs in the back. This one ended up not needing, and this guy here, we have the power cord for the controller itself, and this is where we get our switched power. This braided stainless steel one here is a thermocouple. This is a regular Type K thermocouple that's supposed to be like used okay-ish from like maybe 30 degrees to around 1,000 degrees, something like that. But it has a deviation of around, I don't know, let's just say 10-ish. But at least we get a readout of what it is. It's not the most accurate thing for this application, but it's good enough. And then you see here, I just got one of these janky old like 18 gauge extension cords, and this is what we use for random outputs, inputs, whatever you need to do. This is the switch leg stuff that goes into the controller. Let's just do it. So getting into this guy here. So here we go. Now that we're in here, you guys can see more of what's going on. The part number on this thing, Tango Sierra 2 Kilo. So like I mentioned, I'm not sure if this is an actual Love controller, but either way, it's the same premise. So you can tell here, it tells you on the back side here what your inputs are. So over here would be your thermocouple, positive and negative, which we have hooked up here on the left-hand side with a couple of ferrules. And then over here, our power supply in. So we have our hot leg and our neutral. And then over here are our contacts. So this middle one, where you see this little leg here that would switch back and forth, what we would call the common. And then we have normally closed and normally open. It's almost like we talked about this before. This is an industry standard. So the relay inside of this thing sits in a normally closed configuration. Whenever this is activated, this armature switches to that side and then closes the normally open side of the circuit. And one of the coolest things about this controller is that you can specifically tell it if you want it to control heat or if you want it to control cold. And that would basically switch the output function of this relay. Meaning if something dips below your set point, you want it to turn on. Or if something goes above your set point, you want it to turn on. That's basically how this thing works in essence. Now, you guys see this, electrical taped stuff up here. What I have going on with this fuse holder, like I mentioned, I originally built this thing to test 120 volt heaters. That's clearly not what I'm using it for here. But the way I did this was simply piggybacked the 120 volt from the wall coming into the controller, and I ran it through this fuse holder. So I would have 120 hot on one side of this fuse all of the time, and the other side of the fuse holder out would go to the other side of the relay. So for anything to turn on the output side of my relay, that output power would have to go through this fuse first. It wouldn't simply just take supply power from the controller. It would have to go through my fused circuit first. Right now, I am not utilizing this because to turn on and off that coil, all I needed was a simple closed relay. I wasn't supplying power, I was simply turning it on and off. Now, could I have left this fuse in line and utilized it? Yeah, but whatever, I don't know. This, like I mentioned, this is a test tool. That's all there is to it, not much fancy. Now we might as well go ahead and plug this thing in so I can show you guys what the dealio is, Emilio. So right there, you can tell, we display temperature. So evidently it is 58 degrees in the garage. I'm sorry about this thing flashing like this. This is just the way that a camera picks up an LCD screen. I promise it does not flash like that. That is just the way that the frame rate of this camera picks up this screen. So it doesn't normally look like that, I promise. But here we have the thermocouple. If you go ahead and hold it in your fingers, you'll see this thing starting to climb. And if we put this thing under like a lighter or a torch or something, you'll really see it go through the roof. Now, there was a big jump there because the refresh rate on this thing isn't fantastic. It's probably every like 5-8 seconds or something. But if we go ahead and let this thing go, now, it'll take a while, but eventually this will start to drop again. This reflects actual temperature of this thermocouple. Now, here comes the fun stuff. You can tell here that there's not much going on here on the display. If I want to set this thing, you hit set, it displays SP for set point. You hit it once more, this is your set point temperature. You simply go up and down, select what you want it to be. Once you have it what you want, hit set one more time till it displays SP, and then set and down, and now you have a new set point. Now, like I mentioned, you can change this thing to where you want to control hot or cold. Now, in order to do this particular one, it is different for every controller. This is not gospel, but this particular one, you need to enter the whole menu. not just a set point, you need the entire menu. Now, in order to get into the menu, you need to get back to where this is displaying your current temperature. And then you simply press set and hold for 8 seconds. Once you see this thing pop up as 0, this is, hey guy, put in the code. So you can have like a lockout code on this if you want to. But this one, it's factory set at 0. So we'll go ahead and hit set again, meaning that that's the code that I entered. And now we have access to the entire menu. This first one, now you're gonna have to forgive me, I don't remember exactly what all of these are called, but R0, this is how you set your differential. So let's say I have this thing set to 35 degrees. I don't want the differential to go any more than 2 degrees in either direction. So for R, I would put in 2 degrees and set it. That is my R0, that is my differential temperature. Now going on down here, once we get past some more of these set points here, DO, which I'm assuming means digital output. That's really the best case I can find there. We press set, open this, and you see how it says CO for cold. So we're controlling cold. You press up or down, HT for heat or hot. This is how you control the state of this relay, how you want it to react to your set point. So do you want it to be hot? Do you want it to be cold? In this particular case, we're controlling a refrigerator. We want to control the cold side of this reading. So we're going to go ahead and switch this to cold. Set it and forget it. Now we keep on going down here. This C0. In the short video at the beginning of this, I mentioned that you can set a timer or a safety or an alarm to keep your compressor from short cycling. This one right here, CO, this is your compressor output because this thing is made for heat control and knows probably what you're trying to do. Once we open this thing, it gives you a value of 0 to like 900 or something. And this is in seconds. So however many minutes you want this thing to be off for, you simply do the math times 60. So right now we're set at, what is this, 8 minutes? So the way that this works is this compressor timer thing runs from the last time this relay switched off. So whenever this thing sees a down pulse or like a low peak of this relay, so let's say it's on, it's running for 10 minutes, it shuts off. As soon as it shuts off, this timer starts. So that timer would start at 0 and run up to 480 seconds before this relay is allowed to start again. Meaning this keeps your compressor from short cycling. If you guys know anything about compressors and refrigeration, you cannot have a compressor turn on and off, on and off, on and off. That's detrimental to the compressor. It does not like it, it will not work, and you'll grenade that thing really quickly. So this thing keeps that from happening. Let's say you got a bunch of kids over for the 4th of July or whatever, and everybody's in and out of that fridge every 4 seconds, grabbing Huggies and juice boxes and cold pops, whatever. That thing is going to go crazy because it constantly sees a crazy change in temperature. So it doesn't really know what's going on. So that compressor is going to be like, hey, I need to turn on. Oh, no, I'm cold. I can turn off. Hey, I need to turn on. No, I'm cold. I need to turn off. But like I just mentioned, short cycling of the compressor is bad. So by installing or activating this timer or this safety circuit in here, this keeps that from happening. And it's a user settable input. So like you can change this from whatever you want. It could be a couple seconds if you like to live on the edge, or like I think 8 or 10 minutes or something would be more than enough. Or you could put it up to like 6 hours, whatever you want. Just like I mentioned, this particular one is in seconds and it just goes and goes. You just got to do the math for it. But this is a really good integral part of doing this. And I feel like this is kind of what makes this happen. And once we get back out of here, after we do our settings, whatever we want, we keep on going through some more stuff that I'm not exactly sure. I don't remember what it is right now. But then we get to the A's, the alarm circuits. I think there's 3 of them, 5 of them, 6 of them, 7. Holy crap. 7 different alarms that you can set. So you can have this thing, hey, if I reach 45 degrees Fahrenheit, set off an alarm. If I go below 20 degrees Fahrenheit, set an alarm, yada, yada, yada. So there would be an alarm light that shows up here on the screen. And I believe there is a different output on the back of here. Yeah, you see that little white plug in the middle? That is where your alarm output would be. So if you want to hook up like a light or a beeper or a siren or something to this, whenever one of these alarms that you set activate, boop, something comes on, letting you know your beer is probably getting too warm. Man, I know I've been talking a lot, but you know, for as simple as this thing is, there actually is quite a bit going on here. I kind of took for granted just what I had thrown together on the bench here. But I tell you what, if you're still intrigued and you're still around, we're still doing the project. If you don't mind, I'm going to go ahead and throw together a little something here so you guys can physically see this thing working on the bench. I'm pretty sure that I just got a random relay and a base sitting around here somewhere that, you know, even a light bulb would work fine. I don't know. I'll find something. But we are going to use this thing here on the bench to, like, reenact how this thing would actually work. Give me a minute to put something together here. All right, I believe I got you in something together here. Now, please excuse the crudity of my model. I haven't had time to build it to scale or paint it.
Great Scott!
If you guys got that reference, we could be friends. So just for sake of the demonstration here, what I have set up is something similar to how the refrigerator would work, but instead of cold, we are going to use heat because it's significantly easier to generate. So what we have going on here is this yellow cord. Now this is a do as I say, not as I do thing, because this is sketchy as all get out. This yellow cord plugs into an outlet right up here that you guys just can't see. And then we have the neutral and the hot leg going, one of them going to my contactor here, which would simulate this switch inside the refrigerator, or for lack of a better explanation, the compressor contact, because ultimately this is what we're doing, is turning on and off the compressor. And I have this guy set to control this control voltage through the relay and the set point on the controller. So right now you can see that our thermocouple is reading 59 degrees here in the garage. I have my set point set to 125 degrees, meaning if I bring this thermocouple up to 125 degrees, if I have everything put together correctly, it should activate this contact. Let's go ahead and set this thing back to ambient so we can monitor this. Go ahead and give this guy a little go. Like I mentioned, there is a little bit of a propagation delay, but there you go. 168 degrees on the readout. Our contact is pulled in. Now we let this thing sit and cool down. Then whenever this thing gets below 125 degrees, or the set point, whatever you put for your refrigerator, this contact would drop out, shutting the compressor off. So you guys can see this thing dropping down. We'll watch this relay drop out. And there you have it, folks. It is that simple. I'll go ahead and throw a meter on here so you can see what's going on. There we go. Can you see everything here? I simply have my meter set to AC volts, and I have it going into the coil of the contactor, which is essentially the same thing that's happening inside the refrigerator. Let's go ahead and do the same test again. Bring this thermocouple up to our set point, or in the case of our refrigerator, I guess essentially this is the same thing. We're heating it up, so if it's hot, it would activate the compressor. There we go. Well, if it didn't knock my my meter out there. There you go. We see we have 124 volts at the coil. We'll go ahead, chill for a minute, watch this thing drop back down to its set point. Let's just say 35 degrees for your delicious beer fridge. And then whenever this thing gets down to where you want it to be, you want your compressor to turn off. So this thing is essentially doing that. And there you have it, guys. We're back down to our set point, or whatever you have this set at for your refrigerator. The coil drops out, the compressor shuts off, no power at the compressor. This is how your fridge works. Well, I hope you guys thoroughly enjoyed this one. I know it was a little long-winded, and I get to gabbing on particular topics that, tickle my fancy, if you will. But I genuinely hope that you enjoyed it, because I tore this thing apart after I got it working, just to make this video, because of you guys and the interest that you showed in it. Dude, I was absolutely freaking overwhelmed the reaction that video got. Apparently, there are many more like-minded people out there like me that want to keep this stuff alive. And you know, like jerry-rigging stuff in your garage to keep it running forever. Apparently that's a thing that a lot more people are into than I thought. So now, if you guys will excuse me, I gotta tear all that stuff apart that I just did on the bench and put it back in here so I can get my fridge working again and hopefully cool these things down a little bit. But hopefully you guys got something out of this and you can keep your stuff running for years to come. Hopefully you guys enjoyed, and we'll see you on the next one. What am I supposed to do to make this make sense? I can't believe I tore that whole thing apart. I don't know. Come on, you rotten devil! This thing, oh God. This is a lot easier to do the first time. What if, I don't know, do I really have to take this whole thing apart? I'm not pulling this away from the wall. That ain't happening. Not today. Oh, that's better. That's better.